Hello, everyone. Welcome to this session today, which is going to be a very practical one, where we will give you a rundown through building a real-time analytics pipeline with CrateDB and Apache Kafka. So I'm Niklas, I will be your host today from CrateDB. And before we start getting into any technical implementations, let's take a quick look here on that one slide about our use case, what we're going to talk about today. And our case will be here. You can see it on the left side of the image that we have a payment transaction case. So let's imagine we have in retail stores, for example, or also in e-commerce stores, customers checking out, making a payment transactions. So there is a continuous stream of payment events that are ingested into a Kafka queue here at the second step. So we will take that as our starting point, our scenario. And our goal is to illustrate how to do near real-time analytics from a Grafana dashboard. So let's imagine we want to see certain patterns or certain trends, maybe as soon as they happen in the original data directly in our dashboard. And the way how we are going to implement this today is by using several open source components. So we have Node-RED here as a low-code automation tool that reads messages from Kafka queues and then ingests those messages into CrateDB, so our persistent data storage, which is going to serve us also as a long-term storage. So we don't only have the opportunity to do real-time analytics as changes happen, but also store data for later comparisons, maybe on different type of aggregation levels. And then finally, we would see how Grafana can connect to CrateDB and then visualize the data so that we can generate our insights from those payment transactions. Okay, so that being said, let's jump into the implementation. And as mentioned, our first component is Node-RED. So Node-RED is going to help us take messages out of the Kafka queue and transform them in a way so that we can ingest them into the Crate database. And it's a fairly simple process consisting of these steps here that we will now go through. So first of all, we have a connection to our Kafka queue defined here. And let's quickly enable a debugging mode here so that we get an idea of how these payloads look like that's ingested from our transaction points. And so this is one single message here from our Kafka view now. And what we can see here is some metadata from Kafka. So for example, the topic that we subscribe to, the offset and the partition. But most interestingly here with the value key, we see the actual payload that comes from our transaction event, which is again a JSON document. And taking a closer look, what kind of attributes we have here, we have, for example, a customer ID who made that transaction. We have a category that indicates what type of transaction, what type of merchant was used here. So this was a transportation transaction, maybe someone buying a train ticket, for example. Then there is an age category, which tells us here, so this is an ID, a little bit of additional data about our customers in an anonymized way. And finally, also the amount of the transaction. So this was a €31.53 transaction. Now, as we can see here, there are quite a few messages and events coming in from our data producers. And first of all, we want to streamline a bit the content of this actual event, because when later ingesting the data into the database, we are maybe not that much interested in the metadata from Kafka that we see here. So the next steps here brings us to a function element in Node-RED. And This gives us the possibility to use plain JavaScript to modify the original payload that we get. So what we need to do here first is parse this original value payload here that we got, which we do here in the first line. And then we do a little bit of simplification. So we remove the keys here, for example, because later on when we do the ingestion to the database, we're going to map the position to our columns. We will see how exactly that works later on. But this is always great to have the possibility to clean up the data, modify or transform it in a way so that it's suitable for your data model later on in the database. And so we still right now have individual messages as we take them out of the queue. And when talking now about persisting them in a database, the next step here, which is called batch rows, is a very significant one. Because from a database perspective, just forwarding these individual events directly as insert statements, for example, to the database is typically not the most performant ways because there is some overhead for parsing the SQL statement, for planning the execution, and then for sending to the correct database node, because CrateDB is a distributed database system, the individual messages. And this is why to really get good performance out of our database, out of CrateDB, we batch those rows. And typically there are two different attributes here as part of this. We configured here, for example, that after 10 messages, Node-RED is going to forward a batch then of the cardinality of 10 messages towards CrateDB. So this way we can make sure that we don't get every single message directly to CrateDB. And in case there is maybe a period of low traffic where maybe there are no 10 messages in a reasonable amount of time, there is also the possibility to specify timeout. So in this case, if after 5 minutes here, no 10 records have accumulated, then Node-RED will just forward these statements that have accumulated to CrateDB, even if it hasn't been 10 elements. And if we quickly enable our debug output on that one, then we should see, right here it is in a short amount of period, our array now. So these are 5 elements now, or 10 actually, 10 elements with the values that we extracted from our actual payload. And as we can see here, we removed the actual key, so we only have positional indexes for the different attributes. So this is now already in a great format to proceed ingesting that into the database. So the next step that we do here is we generate the HTTP body of a post request. So CrateDB has 2 different endpoints. You can connect with any Postgres client and do regular SQL inserts, or there's also the option to use an HTTP endpoint, which we are going to make use of here, where we define our statement, which is a plain insert statement into a table called payments. We list the columns here that correspond to the positional index in our nested array, and then the nested array of our 10 messages here that we just saw is then passed here as a bulk argument. And this finally gets executed as an HTTP post request. And this is actually already all we need for ingesting the data out of our Kafka queue into CrateDB as our persistent storage. And as you can imagine, the complexity here can, of course, vary depending on the transformations that you might want to do. But typically, this is the pattern that we see for these types of near real-time data pipelines. So reading the messages out of a queue, batching them to make sure that we are making efficient use of our database, and then sending them through a driver, being it HTTP or Postgres, to the database. Now, looking at that database, we switch over to our CrateDB admin interface. So this is now our payments table where the data ends up. And here we can click on query table and just get a quick sample to see how the data looks like. And that looks now pretty familiar to us. So we add a timestamp here as well when that transaction was taken. And we see our attributes from the raw Kafka payload before, customer ID, the category, the age category, and the amount. So looking back at the table here, there is some additional information in that box on the top. So for example, we see that we have 12 shards here, and this is an interesting concept here of CrateDB for these time series data that we have. So we handle this amount of data by breaking down tables into smaller shards. So in this case, the nearly 40,000 records that I have right now in that table is broken down into smaller pieces, which means shards in our case, and those shards are distributed across different nodes because CrateDB is a distributed database. And we can see this pretty nicely by switching over here to our shards view. So this deployment consists of 2 nodes that you can see here showing up as rows in that view. And as you can see here pretty nicely, these shards, which are indicated by these green rectangles, are to 50% distributed on one node and the other 50% on the other node. So that means data is split equally across the 2 nodes. And this is going to be pretty helpful for our real-time analytics use case, because it means that when ingesting data and when writing data to the shards, the node that retrieves the batch of rows to write will then look up where the data should go to which shard, and will then forward those rows to the corresponding target node. And that means that we can assume the ingest load will be distributed also by equal 50% to the 2 nodes that are involved here. And this is going to be helpful for the ingest performance, but also later on for our analytical performance, because when a select query comes in to read the data, it can also be parallelized very efficiently by running in parallel on multiple shards. So looking back at our table, the next part that we see here is our partitioning. And time series tables have the attribute usually that they grow over time because new data is continuously appended. So one of the questions how to remain performant is how can we make sure that index structures, for example, don't grow indefinitely over time? And this is where partitioning is going to help us. So we partitioned our table here on a daily interval. And that means that for each day, we create 4 new shards in our case. And this way we can make sure that the shards only grow for a definite period of time. So if a day has ended and a new day starts, those shards get rotated, 4 new shards are created, and we can make sure that we have only a limited amount of data in those shards, and our index structures don't grow too large, and therefore we can be sure that also querying them later on in our dashboard is going to be very efficient. And apart from that, we also see our table schema here in our admin UI. And this is exactly what we just saw when we browsed the table with a simple select statement just before. All right. So we see now that the data has arrived in our database. So let's go to the next step and see how to analyze the data. So this is now Grafana, another open source tool where we have a few basically analysis to make some sense of the data that's coming in. And I've set it now to a refresh interval of 5 seconds. So Grafana sends every 5 seconds one query for each of these panels to CrateDB. And that is also why you can see, if you look closely here to those lines, that they change every now and then because a new data point is added. So we can see here the real-time aspect with a maximum delay of 5 seconds. And if we take a closer look of what is behind those panels, then these are pretty much standard SQL queries. Nothing too specific here. So we're doing a select based on our age category and summing up the amount for the selected date range, and also doing a join here to resolve the numeric ID that we got to a human readable label. And also here again, the distributed nature of CrateDB with our sharding helps, because these queries now get sent to the database pretty often, so every 5 seconds, because of our refresh interval. And if we look here at the execution time that we see at the top, we are somewhere in the range of less than 200 milliseconds. And this is because we can parallelize the processing of the query to 4 shards, because we had 4 shards per partitioning per day, and we're querying here data for the last 50 minutes. So we are within 1 partition and therefore 4 shards. So the numbers here are maybe not entirely representational, because of course it's a local setup here now, all running on a Docker Compose setup, and in practice, of course, this would be scaled up quite a bit, but I think it still shows the point that latency here is pretty low, and depending on the scale of the cluster, can definitely also be reduced further. Now, at the bottom, we also see a few more metadata that's interesting to understand the latency and the real-time aspect of our dashboard. So the first one here, the average CrateDB ingest processing time, actually looks at the jobs log of CrateDB, where all the processed insert statements are stored. And when we calculate here how long it takes for such an insert statement to be processed, we see that this is also extremely fast, so in the range of 26 milliseconds roughly. So that's the amount of time that the database needs from receiving the insert statement to actually having finished processing and making the data available for querying. And we can see that this is really an extremely short period of time that is not going to pose a problem for our near real-time analytics. The number that we see here at the bottom is the total end-to-end delay, and that is right now at what you can see here around 4.5 seconds. So this measures really the time that it takes from generating a transaction, so the timestamp that is associated with our payment transaction, to the current timestamp. So it includes the processing of the message in Node-RED, and the processing of the insert statement in CrateDB that we saw here, the on average 20 milliseconds now, plus the potential up to 5 seconds delay in Grafana here when data is reloaded. And as we can see, that stays pretty stable around 4 seconds. And again, this is purely local setup on a desktop machine with fairly restricted resources. So I think the number is actually pretty good for such a setup, and illustrates that it's definitely possible for such dashboards to really have an extremely small delay. So we have a 2-node CrateDB cluster in practice, especially also for fault tolerance. We usually have a 4-node or 3-node CrateDB cluster, so we can expect the runtime to reduce further. And of course, we would typically also have slightly larger batch sizes than here in this example. All right. And in addition, as we also saw in our partitioning here, the interesting part is that we really don't just have access to the latest data, but since we keep all these previous partitions here from older days, we always also have the possibility to compare, for example, current data with historical data. Typical analysis here is, for example, comparing the current weekday with the same weekday from the week before, or maybe from the month before, to see if there are any trends. So we're not just looking here at purely the real-time data, but also have the ability to compare with historical data. And because we prepare and store all the data in an indexed way, you won't see any performance penalty if looking at historical data as well. So this is not just purely optimized for our real-time case, but also gives you great flexibility due to the distributed architecture of CrateDB to make full potential out of your historical data. All right, and that already concludes our small practical example of how to build a near real-time dashboard by persisting data from a Kafka queue and then analyzing the data in Grafana. So hope you enjoyed that session. Thanks for listening in, and goodbye.